Okay, there we go. So I want to talk about this. The other day, we started looking at the Bohr-Rutherford model of the atom. The idea that the atom is made up of a few different particles. And this is something some of you learned in grade 8, but others of you hadn't. That's totally fine. What are the three particles inside an atom? The particles that the atom itself is made of. Yeah?
Electrons, protons, and neutrons.
Cool. Electrons, protons, and neutrons. Who can tell me something about them? What makes an electron different than a proton? How are they different? Yeah, what do we got?
An electron has a negative charge.
An electron has a negative charge, which means if you bring something negatively charged near it, the electron goes away from it. If you bring a positive charge near it, the electron will come near it. Good. And the proton, it doesn't have a negative charge? It has a positive charge. Okay, so these are charged particles, and they have opposite charges. Is that the only thing about them that's different? Otherwise, are they kind of like the same thing, but one's positive and one's negative? Is it like me and Mr. Alaschuk, where we're basically the same, but one of us is smart and the other one not so much? Is that it? Is that the only difference?
Well, the protons are in the middle, with the neutrons and electrons on the other side.
Good, okay. Another difference is that we find protons. Hey, I'm talking. The other difference is we find protons in the middle of the atom, and we find electrons out around them. That's true. By the way, what do we call that middle of the atom? Yeah, good. Nucleus. Is that the only difference? So protons are positive, electrons are negative, protons are found in the middle, electrons are found out around. I can think of one more difference. You can have a big one. Yeah, what do you got? Oh,
It just flashes.
you got a different one?
It's number 10.
Great. So is that number 10? Oh, number 10. I keep taking it out of circulation, and it keeps sending it back in circulation. I don't know what I'm doing wrong. Oh yeah, what's the other difference?
Protons weigh 1 AMU, electrons weigh like 1 power.
Good. That's the other big difference, is that protons are pretty big, relatively speaking. I mean, they're really, really small. But in terms of these things, they're pretty big. Electrons are real tiny. Yeah.
Can I go see this in here?
Sorry?
Can I go see that in here for a second?
Yeah, you bet. Very good. So, you've got protons, they're big and heavy, they weigh 1 atomic mass unit, they have positive charge, they're in the middle of the atom. We have electrons, they're small, they're tiny, they're like 1,000 times lighter, they have a negative charge and they're out around. What's that third particle again? Protons and electrons, and then neutrons. Good, I heard a bunch of you say it. Good. And what can you tell me about a neutron? What's it like? Yep, neutral, which means you're totally right. What's that mean? No charge. Good. What else can you tell me about it?
It weighs the same as a proton?
Good. So it's like a proton.
Yeah.
A lot like a proton. Weighs about the same as a proton, but it is neutral. No charge. Where are they found?
In the nucleus?
In the nucleus with the protons. They're the heavy stuff. Good. And so you did an activity where we started looking at the periodic table and learning about atoms based on the location on the table. And remind me, we define an atom. We say an atom is either this element or that other element. It's either gold or silver or it's hydrogen or it's copper. Based on what? What's the defining characteristic of an atom? This tells you what kind of atom it is. Yes, sir?
Periodic table.
Yep, where it is on the table, for sure. And what is the thing about them that's different? What defines them? What we say that no matter what, you can change a bunch of stuff, but this will be copper as long as this is true. What's the defining character? Yeah.
How many protons?
Good. How many protons is the single most important defining characteristic of an atom? You can take electrons away, it makes a difference, but it doesn't change what it is. You give gold more electrons, it's different, but still gold. You take electrons away, it's different, but still gold. You can add neutrons, it gets heavier, but it's still gold. You can take neutrons away, it gets lighter, but it's still gold. As soon as you add or take a proton away, it is a different atom altogether. That's the defining character. Does that make sense? Having said that, in a normal, electrically balanced, uncharged atom, right? Like I touched this table, it is not shocking me because it doesn't have a charge. A normal atom that doesn't have a charge, if we know how many protons it has, what else do we know just by default? Yeah, you know how many? Electrons. Because if I'm carbon and I have 6 protons, which means I have 6 positive particles, if I'm neutral and I don't have a charge, I must also have 6 negative charges, 6 electrons. Does that make sense? Cool. All right. And then neutrons gets tricky, doesn't it? How do we have to figure out how many neutrons there are? How do we figure that out? Now, what do you got?
You run the mass to the nearest pole,
Good.
and then you minus your.
Isn't it great? That's a good atomic, right?
Atomic number
Yeah.
from the mass to get how many neutrons.
Yeah, that's exactly right. That's a perfect explanation. We have to look at the mass. Because the neutrons can be a little funky, the way we figure out the mass, or the number of neutrons, is by looking at the mass. Because there's only 2 heavy things in an atom. Protons are heavy, and neutrons are heavy. So if we're carbon, and we know we have 6 protons, but we know the thing has to get up to a mass of 12, which we can figure out by weighing the stuff, then we know that there must be 7, 8, 9, 10, 11, 12. There's got to be 6 neutrons in that nucleus as well to make the thing weigh 12. Does that kind of make sense? You guys seem to have done really well with that. I haven't marked that assignment yet, but I've been creeping on all y'all. All y'all. That's very folksy. Very folksy. I don't know if you know this about me.
I say y'all too.
But I've been creeping on your work, and you guys seem to be doing a really good job. So today I want to look at a last step, which is how we can look at the periodic table and get useful information just about an atom from the table without even having to look at the numbers. I don't want to say that I'm a guy who just looks at the pictures when I read a book, but if a book's got pictures, I don't see a whole lot of reason to read those words, if you know what I'm saying. Picture book. It's nice when you have little kids in the house, because then you can read picture books again and nobody can judge you. Right? But anyway, so I want to look at that. So let's take a look here. What we're going to look now is how we can get information from the periodic table. So I want to do just this thing. Here we go. And somebody pick a relatively easy element from the periodic table. What should we do?
Nitrogen.
Oh, nitrogen's good. Okay, I like nitrogen. Do you have your paper periodic table? Awesome. Can you tell me from that what the atomic number of nitrogen is? 7. So that 7 means I need to put what in here? 7 protons. Okay, so I'm going to take a proton. Oh, I failed. 1 hydrogen, 2 helium, 3 lithium. By the way, are these stable yet? No, they're not stable. I don't know why that's not turning on, but that's okay. 4 beryllium, 5 boron, 6 would make it carbon, but 7 makes it nitrogen. Okay, there we go. That's pretty good, but not stable. That's okay. What else do I need to put in this thing if it's going to be, a proper nitrogen? Yeah. Neutrons and electrons. Okay, is one of those easy to figure out? Electrons. How many electrons should I have? 7. Okay, good. So we'll go 1, 2. Hey, the next one I put in, is it going to go in that first shell? No. Why wouldn't it go in the first shell? Oh, the first shell only holds 2. Okay, so it's going to go in the second shell. 3, 4. By the way, this is saying I'm a positive ion. What does it mean by that? Yeah, it means right now this thing has a charge. And because I've got 1, 2, 3, 4, 5, 6, 7 positive charges, but only 1, 2, 3, 4 negative charges, this thing is still positively charged. I can add a 5th electron, still positive. I can add a 6th electron, still positively charged. But then if I add a 7th, now we have a neutral atom. But it's still telling me it's not stable. Why isn't it stable?
You need neutrons, and then
Great.
there will be 7.
Why will there be 7? Why will there be 7? How does she know that? Is she just like just a super nerd and she went home and memorized all the atoms? I think she did.
I'm looking at the thing.
Does she just know that it's always the same as the number of protons? No, it's not that? Then how does she know? What, is she just way smarter than I am? Don't answer that. Yeah.
Because the mass number is 14.
The mass number is 14, and so we have to add 7 neutrons because we've already got 7 from the protons. So this will bring our mass to 8, and bring our mass to 9, and bring our mass to 10. and bring our mass to 11. Oh, see, I didn't notice that. You can put that on there. And bring our mass to 12. Bring our mass to 13. Still doesn't like it. And then it just so happens that stable nitrogen, the most common stable form of nitrogen, has a mass of 14. 7 protons, 7 neutrons. And there it is. That doesn't mean, by the way, like we said, the neutrons do change. There are nitrogen atoms out there that have a different number of neutrons, but this is by far and away the most common one. There we go. You guys did great. Good job. Now, really quickly, I want to tell you, when you look at the periodic table, maybe you've noticed something. It's kind of funkily shaped, isn't it? Like, it's kind of this goofy shaped thing, right? Like where you've got the first row, and the first row only has 2 things in it, and they're really spaced out. And then the next row has got 8 things in it, but it's still got this big stupid gap in it. The row after that has the same big stupid gap. Then the 2 rows after that are full. And then the 2 rows below that, this doesn't even show it. But on your periodic table, what's true about these 2 rows down here? Can you see they're actually even longer, and they've got like a little section that is supposed to be in there that they've drawn below it? You see that? Those 2 bottom rows actually fit inside the periodic table here. So there's supposed to be an even bigger gap in the periodic table, and they just don't draw it that way because they need really big paper, right? So the periodic table is this weird shaped thing. Why? Why is the periodic table drawn this way? I know. That's why I'm here, to tell you, and then you'll know, and then we'll know. And won't that be nice? Yeah. Oh, yeah, you're exactly right.
And then the next 2 are 8 and 8, so those would go in the 2 orbits.
Yeah, that's exactly right.
You explained this to me.
Oh, did I?
Monday.
Did I do a good job? Did you sound like you really get it?
Yeah.
Good deal. Good deal, I'm pretty good. Yeah, no, that's exactly right. Like, you could be up here teaching this thing. I'm not going to let you because I need to get my paycheck. But like, you totally, yeah, I need a believe me, I need a job. But no, that was perfect. So, yeah, I want to take a look here. It's actually really good. The periodic table is all about electrons. It's all about electrons because chemistry is all about electrons. And if you want to understand why that is, when atoms bump into each other, I mean, just think of how an atom is built. Chemistry is all about taking atoms and making them bump into each other and do stuff, right? That's how you make things blow up. That's how you catch things on fire. That's how you make the molecules that cure diseases. That's how you build proteins. That's how you do all of it. It's all atoms bumping into each other. And just look at it. If this is floating around and it finds another atom and they bump into each other, what part of the atom is going to bump into what part of the other atom? Yeah, the electrons. You're not going to bump into the nucleus because the nucleus is tiny and way down in the middle. You're going to bump into the electrons. Chemistry is all about electrons. By the way, sometimes we do actually do reactions that change the nucleus of an atom. That's a whole different type of physics. It's a whole different type of reaction. What do we call those reactions? What kind of reaction is it when you actually change the nucleus, when you actually have protons bumping into protons? Yeah, nuclear reactors. You might have heard of nuclear reactions, nuclear explosions, nuclear power plants. Those are reactions where you're actually using enough energy to make protons bump into the protons and the neutrons bump into the neutrons. But that's not chemistry, or at least it's not chemistry the way you're going to learn it in high school. Basic chemistry, normal chemical reactions are all about electrons. All about electrons, which means if you understand an atom's electrons, you can understand how it will behave chemically, and you can make it do what you want it to do. Does that make sense? Chemistry is all about electrons. So the periodic table is drawn the way it's drawn to tell you about electrons. That's its job. Does that make sense? I can't actually see any of you because I'm being blinded by the projector right now, but are some of you nodding? No. That hurt my feelings. But I'm going to assume that some of you, I see at least one person nodding. It's all about electrons. That's what we want to learn. So, The periodic table is designed to show us the location of electrons. Let's look at what we just drew. We just drew nitrogen. What do we notice about nitrogen? How many shells of electrons does it have? 2. What row is nitrogen in? The second row. Hey, how many electrons fit in the first shell of electrons? 2. Hey, how many elements fit in the first row of elements? Oh, interesting. In the second shell, how many electrons would fit? 8. 10 altogether, but in the shell itself, 8, right? 2, then 8. How many elements fit in the second row? 1, 2, 3, 4, 5, 6, 7, 8. Ah. How many electrons fit in the third row? How many elements are put in the third row of the table? 1, 2, 3, 4, 5, 6, 7, 8. So, if we look, the periodic table is designed to match the way the electron orbitals work. So now, how many electrons are in nitrogen's second shell? 1, 2, 3, 4, 5. Everyone see that? Let's look at where nitrogen is located in the second row. Is it the first element? Yeah, it's not the first, it's not the second, it's not the third, it's not the fourth. It is the fifth element in that row. And it has 5 electrons in its outer shell. So where an element is located on the table tells you about how many shells it has and how many electrons are in those shells. Does that make sense? The periodic table is a map. And so instead of having to look at the numbers and do all sorts of math to figure out what it's like, you can know what its electrons are like instantly just looking at where it is on the table. Can we write that down? Let's write that down. By the way, nobody taught me this until I was like 26 and a science teacher. And then I was like, oh, that's really useful. I wish I'd known that. Which is to say, I'm sure my teacher taught it and I was busy like daydreaming in the back of the classroom. So I'm not like, that's all on me. But just, I wish I'd paid attention in grade 9 science. Actually, I paid attention in grade 9 science because I was terrified of my teacher. But I wish I'd paid attention in grade 10 science. Okay, so here's what we know. So, the row of the periodic table tells us how many electron orbitals and what word do we often use for orbitals? I use it all the time just by habit. Yeah, we often call them orbital shells or electron shells. How many electron orbitals an atom has? All right, that's what we learned from the row number in the periodic table. So, without having to do anything else, without any figuring, if I was looking at, zirconium right here. There's zirconium. How many shells does a zirconium atom have? How many electron orbitals? 5. Let's see. 1, 2, 3, 4. Yeah, 5.
Oh, so the layers is how many things? Oh.
Bingo.
Okay, because I didn't hear you.
That's okay. That's why we repeat it.
So the rows are how many shells it has?
That's right. So silicon. How many shells does silicon have?
3.
Good.
Okay.
1, 2, 3. So silicon, if I was going to draw a Bohr-Rutherford diagram of silicon, how many shells would I have to put in? 1, 2, 3. 1, 2, and then here's the nice thing. The first shell would have to be, full, right? The second shell would have to be full. You only have to worry about the outer shell. Does that make sense? Okay, I'm going to give y'all, 3 minutes to fill these two out. I want to know about sulfur, and I want to know about mercury. Tell me how many orbitals, how many shells they have. You'll have to figure it out. All right, so take 2-3 minutes. Do that.
Better set that up.
Also, hey, do this guy. You gotta bring this thing, right? Keep it up.
Here. Oh, right below the hole. Right below the hole.
All you two fighting this? She fighting it. Right now.
How does that make sense? Oh man.
I have a power. Which is to say, I can beg Chalk and Chalk can have his.
Oh, I found it. It. 1, 2, 3, 4, 5, 6, 7, 1. Wait, no. First there. 1, 2, 3, 4, 5, 6. Yeah, so it's 6. It is 6. I said 6. Why is it called Mercury? Wait, we should have known this. We did the. This is chemistry. I'm so tired of finding the computer. It's all.
All right. So, talk to me. Sulfur. Our buddy sulfur. Oh, Abby, what do you got?
I got it in 3.
You got 3 shells. All right, I haven't looked yet, so I'm going to write it, and that's me putting faith in you, and then we're going to look.
It is.
All right, and if you're wrong, then, whatever. I'll cast you out into the hall with a sign. No, I'm kidding. But where did you come up with that? Because I think you're right. I think you're totally right. How'd you get that number? And what's the symbol for sulfur?
S.
S. So it's this guy here? Awesome. And then what'd you do?
And then I checked what row.
Awesome. And in this case, it's in row 1, row 2. It's in row 3. Beautiful. Nice. Everyone get that? We all understand that, right? We look at the row. It tells us how many shells. Good. Yeah. Sure. Now the next one's a bit of a mystery because Mercury. So I'm looking for what? MC, MR, M, HG. HG Wells' ghost. Why HG? Yes. And that's going to be, that's your,
Why do they have to make it complicated?
this one? This is 4.3C. Assignments. You can go to assignments.
And it's
4.3C.
And there's 5 shells.
All right, let's take a look. 1 shell, 2 shell, 3 shell, 4 shell, 5 shell. Oh, I think you missed this one. It is actually in row 1, 2, 3, 4, 5, 6. But that's okay. That's okay. Listen, if I had $1 for every time I miscounted, I'd have many, many dollars. In fact, I wouldn't know how many because I'd go ahead and miscount that. You done good. Nice. Good work. All right. Any questions about that? So all we need to do to know how many electrons are in an atom, how many orbitals rather are in an atom, is just count down. Now, the nice thing is, anytime we go to draw one of these, this shell will be full for Mercury, this shell will be full, this shell will be full, that shell will be full, this shell will be full. The only shell that is ever not full is the last shell. And that is what moving across the table can tell us. Counting across the table tells you how many electrons are in the final shell. Yeah, and I'll show you, don't worry. Tells you how many electrons are in the outer shell. And maybe you've come to this, maybe you haven't, but did anyone get a chance to find in their work, that little assignment, what we call the outer shell? There's a word for it. There's a word.
It starts with a V.
It does start with a V. Followed by an A. Sorry? Yeah, the outer shell has a name. We call it the... Is that they're just picking random VA words? Vanadium? Vandals?
Where is it?
Varsity? Vicarious? No, that's with an I. Vacuous? Vacillate? Ooh, that's a good word. Do you know what it means to vacillate? It means to be like wishy-washy. It means like to not commit. Yeah, what do we got?
I don't know how to pronounce it, but isn't it like valence?
It is, and you pronounced it beautifully. Good job. We call this the valence. All right, and sometimes they call it the valence shell or the valence orbital, and sometimes they just call it the valence itself. But if you see that word, shh. And if you take chemistry, you're going to see this word a lot. When you see the word valence, it's talking about the outer shell. And again, when you think about chemistry as being atoms bumping into each other, when two atoms collide, not only is it electrons that collide, really, which electrons collide? Well, the outer shell, right? The outermost shell is going to be the thing that comes into contact with the other atom. So the valence is what chemistry is all about. So you just have to count across. By the way, some people will like to teach this by saying, like, look at the column number. The problem with that to me is, like, if you look here, this is column 18. But does helium have 18 electrons in its outer shell? No, so I don't love the column number way of thinking. Or maybe it's just that I'm a big fan of counting things on my fingers, because that's about the level I'm operating at. But to me, just count. If we're looking at helium, it's in the first row, but hydrogen's the one that has 1 electron in its valence. So helium is the one that has 2 electrons in its valence. Does that make sense? Let's take a look at copper. How many electrons does copper have in its valence shell? I don't know. 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, beautiful. It's got 11. So copper has 11 electrons in its outer shell. Yeah. Oh, do we? And are there none in there? Are there none in the? I am so. Mr. Lastchuk, do you mind grabbing? And do you want to grab like 3 just to play safe? Is that okay? Thank you for letting me know.
In that case, it does work out to be the...
Right. Yeah, because it's in the bigger group. Okay, so listen. Shh. Look here. All you have to do is just count over. If you count over, it tells you that. So oxygen, how many electrons in its outer shell? 1, 2, 3, 4, 5, 6. Just count over, right? 1, 2, 3, 4, 5. Oxygen would have 6 electrons in its outer shell. Now that doesn't mean it has 6 electrons total. It doesn't. It has 8 electrons total. But this tells you how many of those electrons are in the outermost shell. So if I was going to draw oxygen, drawing oxygen would be easy because what row is it in? It's in the second row, which tells me it needs how many shells?
2.
So it's going to have a shell and then a second shell, just like that. And then the first shell is always, any shell except the outer one's going to be full. How many electrons fit in the first shell? And the great thing is, if you forgot how many electrons fit in the first shell, what could you look at? The periodic table. 2 electrons in the first shell. So I'm going to put 2 electrons there. And then how many electrons does oxygen have in its outer shell? 1, 2, 3, 4, 5, 6. And I like to draw them in pairs at north, south, east, and west, like at the compass. So 1, 2, 3, 4, 5, 6, just like that. That would be oxygen. See how quickly I did that? Did I even have to look at the numbers on the table? No. Now, if I was going to put the information in the middle, would I have to look at the periodic table?
Yes.
Yeah. Now, I happen to know that oxygen has an atomic number of 6, and it has a mass of 12.00011 AMU, which means it must also have 6, but that's because I've been doing this a long time. You would probably have to look at, no, not a big brain. There's nothing big brain about knowing stuff. You just do it. How do you make glass in Minecraft? What do you do?
What? You said
See? And did you have to think about that, or did you just know it instantly?
I knew
Exactly. Because when you do something enough, you just know it, right? My sister wouldn't be able to tell you how many protons and how many neutrons carbon has, because she's not a chemist. But I'll tell you right now, she could tell you who scored the game-winning goal in the 1952 Stanley Cup. You know what I mean? Like when you deal with something a lot, you know it. You memorize that information. So, Bill Barilko, by the way. So, was that 51? I don't know. Oh, see, now I don't even know. Never mind. I take it back. So anyway, here's what we're going to do. I want you to take a look at chlorine, and just based on its location on the table, I want to tell you how many shells, how many electrons in the outer shell, and then if you could even draw a little sketch of it, that'd be great. All right? And then you're going to do the same for manganese, and then you're going to do the same for gold, though these are pretty big, so you might not want to sketch them. But you could. All right, so take a minute and do that. I'll be walking around saying encouraging things like "good job" and "hey, not bad." Actually, that's not true. Whilst you do that, I am going to find that in the hooch. So we're ready to go. Ooh, let me see. It's really hard. Yeah, it's really hard. I acknowledge that. All right, get those filled in. Get those filled in. Manganese, not magnesium. Manganese. I'm ready. All right. Winningest. It's kind of a weird word, isn't it?
It's not even a real word.
All right. Hey, we got this. If you don't got this, get focused. Get it figured out. Ooh, great. Can you show me?
So my grandma's house is cool.
Beautiful.
I know it's on the bottom. It's eight.
So let's look at this one.
Okay, I'll close. I'll close.
Chlorine's here. So talk about it.
Actually, no, no.
Good. Yeah, beautiful. Yeah, fantastic. You can count. I know you can count. You should. Also, you can count on me freaking out if you don't keep this up over your nose. Okay, we can go there. See what?
They use acid.
Yes.
Ew. Both made by
Gold is it comes from the Latin gold is aura.
Can you show a picture of making that outer shell again for a second?
Yeah. What?
Oh, yes. We read it.
Like this one?
Yeah, thank you. See that? No, see the outer shell? Not the outer shell.
Ooh, can I get your pointer? Oh, I'm terrible at this. I'm blocking. That's it. Oh, yeah.
I actually did it. No, I'm not. I'm surprised I'm not failing.
Sorry?
I'm surprised I'm not failing.
I'm not. Clever kid.
I don't get how.
Your phone's away or I'll make you chew on them.
Oh yeah?
Yeah. Seriously, put away. Away.
In your bag. I don't even know what.
You're sitting 3 feet from me on your phone. I'll fight you.
You think I would kill my phone?
I said put them away. I didn't mean right there. Put them away. Put them away. You can keep them put away or I'll take them. I haven't done my phone rant yet, but oh boy, are you going to hear it. All right, can I have your attention here? Can we try this together? Is that all right? I'm asking you. I was asking you, the collective you. Okay, let's take a look. So, here we are, and we want to look at chlorine. Oh, I like it up here.
Why?
Is this what being tall would feel like? This is nice. Yeah. How tall would I? No! Oh no, are you allowed to cash my paychecks and drive my car back to my house? No, then you don't get to stand on the chair either. When you become me, then you can do what I do. For now, you do what you do, I do what I do. That's how this works. So what you do when you get a job, we'd be like, oh, what, so do I get to own the company? No, you don't. Until you work there long enough, then maybe you can.
I can't eat so many donuts that I have a phone on the side of the room.
That's a you question, but don't do it in here, please. I haven't lost anybody yet, and you're not going to be the first. All right, so let's talk about chlorine. First and foremost, what's the symbol for chlorine? All right, Cl. So let's take a look. Where on here am I finding Cl? Third row, first row, second row. It's somewhere in this row. All right, and oh, I see it. All right, so there's chlorine. Where do we find chlorine? Third row. What does the fact that it's in the third row tell me? It's got 3 shells. Okay, good. So look, they put it in the third row the way it's arranged to say it's got a full first shell, it's got a full second shell, and then it's got a partial third shell. So we know it's got to have 3 shells. Which means, if I was going to make a Bohr-Rutherford diagram of this, I'd have 1 shell, 2 shells, 3 shells. Hey, what do I know about that first shell? It's got to be full. What do I know about the second shell? By the way, would you ever make such a disgustingly messy Bohr-Rutherford diagram?
Yes.
You most certainly would not. But here I am. Okay, now how would I know how many electrons go in that outer shell? By the way, hey, what do I call the outer shell? The valence. The valence, good. So how many electrons in there? Yeah.
It'll be 7 because it's 7.
Good, okay, let's take a look. Because when we count over, sodium has 1, magnesium has 2, aluminum 3, silicon 4, phosphorus 5, sulfur 6 rather, and chlorine 7. So that means there's 7 electrons in its outer shell. Which means when we go to fill the valence in, we'd go 1, 2, 3, 4, 5, 6, 7, not a full shell. Close to a full shell, not a full shell. Cool. All right, manganese. Did anyone find that?
Yeah. Is that in the third row, MG?
Ah, very close. Mg is in the third row. It's a real thing, but that is actually magnesium. And this is the annoyingly similarly named manganese. Mn. Very good. So we're looking for Mn. And where do we find Mn? Fourth row. All right, let's take a look. We find it right here. So fourth row. So it's got 4 shells. Hey, I'm not going to draw a Bohr-Rutherford diagram of this because it's a pain in the butt. But how many shells would I need? Yeah, if I was going to draw this, I'd have to draw the nucleus and then 1 shell, 2 shells, 3 shells, 4 shells. I'm not doing that. I've got my grade 9 credit, thank you. How many electrons in its outer shell? 7 again. That was lazy of me. 1, 2, 3, 4, 5, 6, 7. By the way, I picked that number twice in a row to show you that they don't necessarily have to be in line with each other to have that same number of electrons, right? Because different size shells. So, this has 7 electrons in its outer shell. And lastly, let's look at gold. What's the chemical formula for gold, or the symbol, I should say, for gold? Au, from the Latin aura, however you say it. I don't know how you say it. What row do we find that in? Gold's a big guy. It's a fairly big atom, yeah. It's in the 6th row, which means it has 6 shells of electrons. Lots of electrons. Big, heavy atom. Gold is heavy. I've never been in a position to pick up a bar of gold, but like a bar of gold would be substantially heavier than that same bar of steel. Substantially heavier. It's a big, heavy atom. Yeah. Great. How many electrons in its outer shell? 11. And how did you get that? Yeah, so we find AU there, and we say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
I didn't really count over, but I would have. I just used
Great. The truth is, if we actually want to get into it, it actually has a few more because of the way the periodic table is set up, but that's okay. For the purposes of today's work, because if you actually look at these two rows are interesting because they include a little punch-out. So you actually have to include all the bottom ones.
25?
Yeah, so it's actually a better answer would be 25 because we have to include those mini guys in the bottom. But I'm not too worried about that. We don't deal with the big things on the periodic table very often because they get complicated. And I'm not a complicated guy.
So we just use like the first.
Mostly. And that's mostly what we deal with. Okay, now I'm going to introduce you to something to make your life a little easier. Bohr-Rutherford diagrams, pain to draw, aren't they? Kind of a pain? Yeah, a lot of information there. But I told you that chemistry is really all about what? What is involved in chemistry? Chemistry is all about electrons. And specifically, when two atoms bump into each other, it is the electrons that do the reacting, and even more to the point, which electrons? The valence, right? That outer shell of electrons. So if you want to know how an atom will behave chemically, all we really need to know about is that outer shell of electrons. Does that make sense? If you know about that, you've got it figured out. So, what if we drew a Bohr-Rutherford diagram, but we took out all of the full shells of electrons, all the unnecessary shells, and we took out the protons and we took out the neutrons. What would be left in our diagram?
The electron.
Just the valence shell. Does that make sense? So let's take an example. Give me something in the 2nd row. Actually, can we do carbon? Because we got carbon right here. Does this make sense? So in this diagram, what actually matters for this thing's chemical behavior? We said it's the outer electrons that matter. So I care about the outer electrons. Do I care about this inner shell? Do I care that it has 6 protons? Only in as much that the fact that it has 6 protons means it must be carbon, right? Because that determines what it is. So what we can do is we can say, okay, instead of doing all of this work drawing the nucleus, all I need to tell you is that what's in the nucleus of this? It's carbon. Does that make sense? So in a Lewis diagram, we don't bother saying there's 6 protons and 6 neutrons. We just say, hey, it's carbon. Cool. And then, this oxygen, isn't it? Yeah, I'm just gonna do some real quick cheating. Now it's carbon. Now it was carbon the whole time, wasn't it, guys?
No.
Carbon the whole time. Always carbon. Always carbon. I was never wrong. I'm the teacher. Sorry about that. Okay, so we got carbon in there. And now that we know we have carbon in there, because these are 8s and they were always 8s. Yeah, because we've been talking about carbon this whole time.
Carbon has 6.
Oh, you're right. Oh, I'm getting all confused. Oh, gosh, I'm fired. That's it. Brady, class is yours. You teach it. I'm out. You got this. I have to? Fine. Okay. So sorry about that. Instead of drawing all this, we just draw that. And then we don't worry about the inner shell. We just care about the outer shell. And in this case, how many electrons does carbon have in its outer shell? 4. And so we just say 1, 2, 3, 4. And we don't even draw them as little e's or little negative signs. We just use a dot. Isn't that nice? Pretty easy, right? And there's some rules. Don't just draw them randomly. All right, don't do this. Unless you want me to be sad, and you don't want me to be sad. Shh. So the rule is always do sort of north, south, east, and west first, and then double up. So it doesn't, and I really do not care where you start in terms of up, down, left, right, but put them up, down, left, right, like that, and then if you need to, you can start doubling up. Does that make sense? Doesn't matter, you could go left, right, up, down, you could go right, left, up, down. Doesn't matter, but put one in each, then start doubling up. And then if you have to go past 8, which sometimes you do, whatever, all bets are off, just make them fit. But that's it. That's how we draw a Lewis diagram. So give me another atom here and we'll see if I can screw that up royally. Yeah. And stick to like the first, like, okay, aluminum's good. We like aluminum. So here's aluminum, and here's the beautiful thing. All I need to know is it's going to be Al. Do I need to even care that, how many shells does aluminum have? Has 3 shells, but does that matter for a Lewis diagram? No, all that matters is how many electrons does it need? And so I'd go 1 electron, 2 electron, 3 electrons. That's a Lewis diagram. Make sense? That's it. That's the whole thing. A lot easier, isn't it? Sorry? So, let's draw these. The first one is hydrogen. So if we look at the periodic table, what's the symbol for hydrogen? H. And how many electrons does it have in its outer shell?
1.
Just 1. That is a Lewis diagram of hydrogen. An H and a dot. Tells you everything you need to know. Not bad, right? So take 2 minutes and fill those in. See if you can get these filled in. So we said hydrogen looks like this. Yeah, you'll need to draw them. You can use the pen feature. You could draw them. If you want to grab a whiteboard and draw them and then snap a picture, do that. If you want to, like, add shapes, you can add shapes. You've got the power. I have faith in you. I know it's not ideal. I wish everybody, like I say over and over again, every year I try to get the board to buy me a class set of these devices, and every year I fail miserably. Yeah, of course. Yeah, feel free to come up and get some paper and a pencil. Come up and get a whiteboard if you need it. My house is your house, team.
So I can come into your house?
No.
But you just said.
I lied. The thing I did. Wow, that's pretty good. Nice job. So its first shell will be full, second shell will be full, third shell will be full. Why is this a D? You go 1, 2, 3, 4. Does that make sense? Cool.
It's third row 7. So we draw 7 dots.
Oh, sorry, I didn't see that.
So there's 1, 2, 3, 4, 5 dots.
Oh, look at you. One thing that you have to do. Other than that, it's all good. It's all gold.
Oh, 5. Yeah, that's it. 15.
Okay, it's 10:54.
It's 10:53.
It says 10:54.
That's
And even if it was 10:53, it'd be 22. You're adding 2 is wrong.
it's 23.
It says 15.
15 is 23. No, it's not. It's God.
Did you not pay attention?
I'm wrong. I was thinking of 6.
How much?
How are you gonna get better marks?
6.2.
How are you gonna get better marks?
I'm thinking of 3, bro. I was thinking of way far.
It says 15.
Yes, go right ahead.
You know we don't.
Yes.
It says 15. 15. It says 15.
I don't deserve the money.
Are you using the atomic number?
It says 15.
Oh, wow.
It says 15 to 15.
That's not all I bought.
Oh, do you find how much make the ratio?
Oh, divide that by 3.
Doesn't really say anything. My old server always have rank.
I'm trying to watch it.
Click on the number tab and server settings. Where is it? Is it this?
Yeah, we missed more.
Okay, that's fine.
All right, team. All right. Can I look at well, that took a while.
It says 15.
Hold up. Hold up. Okay.
97.
No. Listen, can I explain?
Is that better? 97?
Because because it's actually right. It is 15. It's 15.
See,
Whoa! You're both right. Listen.
15.
It's 15.
Just saying it's above.
I
Do
know.
not
I
let
know.
him
I like
win.
it.
Do not
It makes me kind of happy. So there are 15
It makes me
electrons.
wanna kill him.
There are 15 electrons, but look here. But those 15 electrons are split up into different shells. And the first shell holds 2 of them, and the second shell holds 8 of them, and then the third shell has 1, 2, 3, 4, 5 of them. So to figure out how many are in the outer shell, all you have to do is find it, and just count on over.
Thank you, gold
Yeah,
97.
that wasn't for you, don't worry. So don't worry. You got it, so don't let it confuse you. You're in
You
good shape.
gold 97.
0.97? We'll get there. All right, let's take a look. Okay. Shh. So let's draw a Lewis diagram for each of these. Phosphorus. What's the symbol for phosphorus? Very good. And let's take a look at our periodic table. We find phosphorus in the... Settled in. We find it in the third row, which means it has 3 shells, but we don't have to worry about those because the first shell is full. The second shell is full. We just have to worry about the third shell. How many are in phosphorus's third shell? Yeah, 1, 2, 3. Shh. Settle down. 4 and 5. So phosphorus has 5 electrons in its valence shell. 5 electrons in its shell that is out and actively doing chemistry. 1, 2, 3, 4, and I'm going to double up here for a total of 5. And I should probably have drawn that a little smaller. If you drew it too big, you might just want to shrink that down a bit. I don't know. There we go. All right, sodium. What's the symbol for sodium? So, yep. Very good. You might be tempted to use S, but S is in fact for sulfur. Common mistake. N is sodium. Na is sodium. It comes from its Latin name, which is natrium. So if you spoke Latin, that would make a lot of sense to you. Of course, we don't speak Latin, we speak English, so it's weird. It's weird that sodium is Na, but sodium is Na. On the periodic table, where do we find Na? Where do we find sodium? Right there. So how many electrons in its outer shell? Just one. One lonely little electron. Sodium has a lot of electrons, but not in its outer shell. In its outer shell, it's just got one lonely little electron. What about chlorine? Chlorine we know is Cl. How many electrons in its outer shell? Yeah. Very good. 1, 2, 3, 4, 5, 6, and 7. There's our Lewis diagram of chlorine. And phenol, the shows phenomon. Nitrogen.
What's the thing for mercury again?
Mercury is Hg.
Is what?
Hg. All right, nitrogen, what do we got? What's its symbol? N. And how many electrons in its outermost shell?
5.
Very good. 1, 2, 3, 4, 5. And again, how did we get that? We went up and we looked. We saw nitrogen was right here, and we can just count it. 1, 2, 3, 4, 5. All right. Okay. That's great. We're going to carry on with chemistry in block 2.
Can you stay on that for a second longer?
Yes, you bet. Oh, maybe not.
I can't see it.
Settled in. There we go. So there we go. But what we're going to do right now is a Christmas Kahoot. I'm assuming it's Christmas. I have no idea. I haven't looked at this. Maybe it's about, like, chemistry. I don't know. That doesn't seem very inclusive. What about chemistry? What? I got news for you. I've taught every kid in this school chemistry, and they all care. They all care. Okay. Whoa. So pull up Kahoot, and so guys, I just want to say, this is both a chance to do something fun, which is great, and a chance to bond as a class, which is good, and you have a chance to win a prize, which is nice and looks tasty, but this is also a chance for you to crush my enemies.
I mean, enemies and teachers.
Yeah, that's right. So, yeah, them. So, let's have a good clean fight here, but let's play our hardest, right? Do you want Kelford's class to win this? Is that what you want? Is that what you want?
Funniest name.
Do you want Mr. Kelford's class to be winning this? I don't.
Sure, why not?
Do you want Trush's math class or science class to be winning this right now? Is that what you want to be known as? The class that lost to Mr. Trush's science class? It's not what I want to be known as. No, thank you.